Cool. My name is Carl Steinbach. I work at LinkedIn. I've been there for 4 years. I'm the tech lead for the grid development team, a group of people who are responsible for LinkedIn's offline data infrastructure, including Hadoop, HDFS, Yarn, Spark, and a bunch of things that we've built on top of these different components to make the people who use them at LinkedIn more productive. So today I'm going to talk sort of about the history of Hadoop at LinkedIn because I think it's an interesting story. Some of the things that we've done recently, and also a little bit about where I think we're going to be headed over the next 1 to 2 to 3 years. Before I get there though, I was hoping everyone could help me out with something really quickly. So in this title I reference Hadoop. I think when I use that term, I feel like that encompasses Spark as well, but I'm curious how many people in the room, when you hear the term Hadoop, you think that that's like a distinctly different thing from Spark? Show of hands. Okay, and how many people, when I say Hadoop, basically think, yeah, Hadoop is MapReduce plus Spark plus Yarn plus HDFS? Okay, I would say that's evenly divided then, right? So the marketing people have succeeded. In a way. Okay, so let's get started. So where did this all start? So back in 2006, LinkedIn built a feature called People You May Know. And what does it do? Basically, it just recommends people you may know. And this feature became sort of an instant success. And it was, in many ways, sort of the engine of growth driving new members to sign up. The original implementation ran on Oracle. And that was great, in the sense that it made it, quick to implement, but it also introduced some challenges. So anyway, PYMK fundamentally is triangle closing. If Mary knows Dave and Mary knows Steve, there's a pretty good chance that Dave and Steve may know each other. And you get a stronger graph once they make that connection. So just repeat this 1 million or 1 billion times and you get the basic idea. So, like I said, PYMK was this runaway success. By 2008, they had 10 times as many members. It was still running on Oracle. It failed often, and I think most importantly, it had originally taken, I think, about 6 weeks to run through the entire data set and generate the results. By 2008, it was taking 6 months, which is way too slow. And given the success of this feature and the rate at which the site was growing in terms of members, people could predict with ease that it was going to take 12 months, 24 months in the near future. So the engineers responsible for PYMK started looking for another solution to handle this. And at that time, they had started to hear about Hadoop, so they gave it a shot. When I joined LinkedIn 4 years ago, one of the first things I did was to go and search in Jira trying to find the start of Hadoop at LinkedIn. And there's kind of an interesting ticket where the engineers who got this thing started were trying to cobble together a set of nodes. You might notice that they're using Sun Spark boxes. They're running this on Solaris. And I think one thing that this sort of highlights is in 2008, I think outside of Yahoo, no one really knew how to run Hadoop. There weren't any books available. There were very few blog posts. So it was a lot of trial and error type stuff. If you were lucky, maybe you knew someone at Yahoo and you could get the inside track on what was going on and the right way to do things. But it's taken a long time for the community really to get to a point where I think best practices have been established. And in the meantime, right, we were all sort of addicted to self-harm. I mean, we were hurting ourselves every day, hurting the people around us, creating a ton of tech debt. And I think, a lot of people these days are sort of in the process of not migrating off of really a legacy system. It's more like a set of legacy systems, all of which are tightly intertwined with each other. So by 2009, this experiment with Hadoop had been sort of by general consensus viewed as a big success. Everyone else with similar problems of scale started looking at it. And that sort of brings us to the present, where our cluster footprint has grown quite a bit. We now have upwards of 10 clusters, upwards of 10,000 nodes. And I think sort of the thing I want to really draw your attention to here is that we have more than 1,000 people who've used the platform at LinkedIn. So there's a tremendous diversity in terms of backgrounds of the people who are using it, what they're trying to do with it. And that creates both problems, but also I think a lot of opportunities. If you're interested in addressing issues like user productivity or thinking about how to really make this platform more productive for the people using it. So since Hadoop grew very organically at LinkedIn, there were no real policies or procedures in place governing what people could do on the platform or what they could use to accomplish their work. So there was a well-established pattern of people hearing about something, a new framework, a new utility, a new tool, trying it out and then evangelizing it, spreading adoption. And that led to a lot of great stuff. It also led to sort of a lot of dead ends, which it takes time to clean up. But there's also, I think, at LinkedIn a very strong culture of having the freedom to go and solve problems for yourself if a solution doesn't already exist. And that's led to some great work on things like Goblin and Qbert, frameworks that people have written there. So I think the two main challenges that my team faces today are issues of scale. And I think the issue of scale that everyone is familiar with is how do you scale out machines and the systems that run on top of them. But I think the thing that I've learned over the past couple of years is that when you have 1,000 people using a shared resource, actually scaling their productivity and the processes that connect them together is as hard a problem, if not harder. So I'm going to talk about both of these today. So first of all, let's discuss scaling machines. So one of the things that we've learned is that HDFS at sort of the edge of scale is not as friendly as you'd like to believe. I mean, the whole point of Hadoop is scale. If you read the blog posts about it, the thing that gets people's attention are articles about 4,000 node, 8,000 node clusters. But in reality, the number of organizations on this planet that run at that scale probably represents less than 1% of the overall sites running it. So from our experience, like this sort of leads to a couple of conclusions. One is that the upstream community is really not incentivized to care that much about scale issues that you see when you get to this level. A majority of the code, I think, these days comes from a collection of vendors who don't have any customers who operate at this scale, so they don't see these bugs. They're not really that interested in looking for them in the first place. Another issue with just the upstream release process is that scale testing happens after the release, not before it. So I think, looking at upstream releases with a lot of confidence, in many cases, you can say this probably will not scale without some additional work. So this was all sort of like academic for us until March of 2015. And at that point, we did some things that were, in retrospect, not a very good idea, and we learned a lot in the process. So we added 500 nodes very rapidly to a 2,000 node cluster that we had. And within about a couple of hours, the RPC queue time on the name node exploded. And this prevented jobs from launching because they couldn't compute their splits, and jobs that were running way slower. And the next week was one long fire drill trying to figure out what caused this issue. So we eventually tracked it back to two pretty subtle scale regressions that had been committed upstream, which had been included in multiple upstream releases, and which we later found were actually present in vendor distributions. The interesting thing about these bugs is that they really didn't sort of manifest symptoms until you got to the scale of, say, 3,000 to 4,000 nodes. So in adding these 500 nodes very quickly, we sort of blew past the tipping point and found ourselves in a very bad position. I'm going to take a quick sip of water here. Sorry. So we started, to think about this. We really wanted to avoid ever finding ourselves in a situation like this again. And we thought, how can we do a better job of scale testing before we deploy these upgrades on the cluster? So the sort of like conventional way of doing this is, you start with your small cluster, you deploy it there. If everything looks good after a week, then you deploy it to your next largest cluster and keep working your way up. Depending on how large your biggest cluster is, this can take quite a bit of time. It's expensive, both in terms of the amount of time it takes developers to do this, as well as the hardware, the clusters that you have to treat effectively as test clusters. I think another point is it doesn't always work. You may not catch issues because you're not really running it on a large enough cluster. And I think the biggest issue here is that it's risky. In some cases, upgrades are one way. You can't roll back, so you're pretty much stuck in a bad situation if you find yourself there. So we looked more closely at the name node, realized that that was really the scale limiting bottleneck in the system, and that was the thing that we needed to scale test the most. So we started to wonder about how we could scale test the name node in a cost-effective manner. What we ended up doing was building a framework that allows us to run data node daemons inside of Yarn containers. And this gives us the ability to create an army of data nodes, which are talking to the name node under scale test. And we play one other trick, which is to create a bunch of files which are 1 byte in size. So the data nodes, of course, are not stressed out about this, but the name node is, because the name node cares about blocks. It doesn't care how big the blocks are. The load that it sees has only to do really with the number of data nodes that it's talking to and the number of blocks that it has to manage. So we're able to convince the name node that it sees all of these data nodes when in fact it's sort of speaking to these artificial data nodes. Another nice thing about this approach is that it's completely black box. So we don't depend on any internal APIs, which means that we don't have to invest a lot of work maintaining this as those internal APIs change over time upstream. Now I want to talk a little bit about some of the work we've done to make people more productive on top of the platform. So a big issue for us is performance tuning. I think one thing about Hadoop in particular and the frameworks and components that people use on top of it, and a big distinction between it and things like R or Oracle, is that in R or Oracle, once you've sort of gotten your thing working, you're 90% there. In Hadoop, the distinction between having something that works and having something that works efficiently can represent 50% of the overall time that you have to invest building the thing. And that's, I think, forced a lot of people into this position of either choosing user productivity or infrastructure efficiency. And we found that more often than not, users left to their own devices are going to err on the side of their own productivity. But this then leads to a cluster which is laboring under the load of thousands of poorly tuned jobs. So at the root of the problem really is that Hadoop exposes way too many knobs. Another issue is that even if you get your job properly tuned, by the end of the week it can fall out of tune based on changes in the data. Skew can appear where skew didn't exist before, for example. So there's an ongoing cost just to watch your job and make sure that nothing happens to it afterwards. So we fixed this problem by building something called Dr. Elephant. It's a service which looks at the exhaust of jobs in the form of logs, both from Spark as well as MapReduce. And then it applies different heuristics, diagnostic criteria that it uses to identify problems with the job. And I think most importantly, it then offers actionable advice to users. Basically says, these are the things that you need to change in order to eliminate this problem. So in many ways, it sort of resembles a friendly doctor. You have a sick job, it's going to give you some advice about what you need to do to improve the health of that. So last year, in April of 2016, we open sourced Dr. Elephant. It's on GitHub. I'd encourage everyone to take a look at it. Since we open sourced it, it's been adopted and deployed in production at a bunch of other companies. We've also seen contributions from other companies. And I think one of the more interesting recent developments is that Pepperdata, another vendor, has actually integrated Dr. Elephant into its commercial product offering. We're really excited about this, and one of the main reasons is we expect that these heuristics are going to behave differently when they're exposed to different workloads. So we're excited at the possibility of being able to expose Dr. Elephant to workloads that are not present at LinkedIn, make the heuristics stronger in the process, and also get contributions of new heuristics that everyone can benefit from. So another sort of big issue and bane of my existence is upgrades. We of course want to do upgrades as frequently as possible because it allows us to bring more value and expose users to new features and new improvements that have gone in upstream. But it also causes a lot of problems with version mismatches, incompatibilities, and the like. So a lot of work that we've done has sort of focused on how do we de-risk upgrades, how do we test them to make sure that there aren't going to be incompatibilities, and in cases where there are, predict those in advance, figure out what's going to fail, and have a plan in place. So Hadoop has a big problem with dependency management and class path management. And this issue, I think upstream has gotten incrementally better, especially over the last year. But if you're really paranoid, and at this point I'm really paranoid because I'm tired of getting hurt, I think the safest approach to take is a big hammer like shading. So some of you may be familiar with this. The idea basically is to take some Java bytecode and edit the package name. So you're sort of creating a partition namespace separate from the namespace of the code as defined in the source. I think the interesting thing about shading is that really it's like static linking for Java. If you've written code in C or C++, you know that you have this option of either generating a shared library or you can statically link your code. And back in the day when shared libraries were introduced, everyone was like, oh man, I can save so much disk space. This is awesome. I don't have to have this object code all over the place that's redundant. And then, a couple of years later, especially at places like Google, they realized, oh man, this is shared object hell. I deploy something, someone else changes something, suddenly my service is broken. This sucks. So I think it's pretty well known that at Google, everything is statically linked. They've got enough disk space, they've got enough RAM, it doesn't matter. But what matters to them is being able to say with certainty, like if this thing runs now, it's going to continue to run. It's not going to start failing all of a sudden with a symbol not found error. So that's what we've invested a lot in. I think one of the reasons why, I'll make the statement that I think shading is kind of unfairly maligned. And I think a lot of that has to do with the fact that the existing tools for shading are not that great. So we invested time building our own Gradle plugin, which adds features that makes it easier for people to understand what they're shading and also to understand what they may need to shade as people continue making changes to the code base that's being shaded. Another thing related to shading is a tool we built called ByteRate, which allows us to do bytecode analysis on jar files. So, I sort of talked before about how the early days of Hadoop at LinkedIn were very, sort of like the Wild West. A lot of things were happening. And this led to, in some cases, situations where we have a workflow we have the bytecode for the workflow, but we don't have the original source code. I think another issue you'll see is that with Azkaban, people upload zip files, so they're uploading jar files. And this causes a lot of problems when, for example, a workflow zip includes Hadoop client libraries or jar files that may conflict with what's found in the cluster, or other ways of sort of polluting the class path. So we have ByteRay. ByteRay allows us to audit jars as they're uploaded, looking for things that have been blacklisted. Another interesting thing about ByteRay, when we migrated from Hadoop 1 to Hadoop 2, some of you may recall that there were binary incompatibilities between those two versions, but they were actually source compatible. So this very weird situation of having to ask users, we need you to go basically bump your dependencies against Hadoop and then recompile, but you don't need to change any of your source code. And then please, re-upload your job. That was a big sort of useless task to ask 1,000 people to do. So with ByteRay, we actually just started modifying the bytecode of the jar files that users were producing in order to eliminate this binary incompatibility. And I should also just, I think, quickly add that the binary incompatibility has to do with the fact that in Java, if you change an interface to a class or vice versa, it remains source compatible. You don't have to change anything else in your code. But it is a binary incompatibility for generated code. And that's basically what happened between Hadoop 1 and Hadoop 2. So here's an example of ByteRay in action. In this case, the user has tried to upload a workflow that includes some Hadoop client jars. I'll add that the message kind of implies that we have a whitelist or blacklist of jar files, but we are actually whitelisting and blacklisting class files. So that's what we're looking for in the thing. So another thing that we've built and continue to work on is a system called SoakCycle. The idea is to sort of do integration testing at scale, but more importantly, to do the integration testing against real workloads. Since Hadoop has such a broad API, and since the contracts between components are so complicated and evolving, it's very hard to say whether upgrading HDFS will break workflows. It's very hard to say whether a new version of Pig will cause something to stop working. And I think an observation that we came to is that you can spend all day long, for 1,000 years, writing integration tests for Hadoop and still not catch all of the things that your users are going to encounter. But you could sort of look at what users are doing on the cluster every day, writing workflows, building applications. And in a way, they are your army of QA engineers if you just treat their actual jobs as tests. So the concept behind SoakCycle is we have a sandbox cluster partitioned off from everything else. We have samples of all of the real data sets, and then we forklift jobs from the production or development clusters over to the SoakCycle cluster and basically throw them in a shotgun approach at the new components. And if stuff fails that was passing on the prod or dev clusters, then we know there's a problem. We don't necessarily know what it is, but we know that we don't want to roll this out, and it's something that requires more investigation. So that brings me to the future. The big thing that is going to sort of define what my team works on over the next couple of years is an umbrella project that we talk or refer to as OneGrid. So we have upwards of 10 clusters, and a couple of years from now, we expect to have upwards of 20 or 30 clusters. One aspect of that is that we are planning to solve, for example, the problem of scaling HDFS by, not really scaling HDFS, but just federating over multiple HDFS clusters. So that's, driving us to build more clusters and have to manage more clusters. And once you get to this point, you have to make some assumptions. Like, you're never going to be running the same version of anything on all of the clusters. So you have to develop mechanisms for insulating yourself as well as user jobs from version incompatibilities. Another thing is data replication. We very much want to have a single namespace, both at the file system level, but also more importantly at the data set level, and get people sort of bumped up a level in terms of the API that they use to access data. I think one of the things about HDFS that in retrospect maybe isn't that great is that it really does expose a file system API when what people are actually, for the most part, doing on it is reading and writing data sets, and the semantics of those two operations are quite different. If you bump yourself up a level of abstraction, it makes it a lot easier to implement many types of atomic operations. And it also provides more context about the intent of what users are trying to do. Your logs become a lot more informative because you see, aha, someone is reading this logical data set as opposed to, well, someone's reading a file and I can map that file back to this data set and I kind of know where it came from. So our goal really is to, for users, make all of our clusters look like one big cluster, which means, like I said, a single logical namespace. It also means scheduling that spans multiple clusters. So instead of thinking about it in terms of I'm going to run my job on cluster A or cluster B, you just think about it in terms of I'm submitting my job to this larger sort of logical cluster. That opens the door to many sorts of interesting types of optimization. You can think about cost-based optimization in terms of pre-positioning data so that it, is where it needs to be to increase the chance of a local read. Anyway, that's the end of the talk. Here's some contact details in case people have any questions. And I guess I can also take some questions right now. Anyone? Question in the back. You're asking about ByteRay? ByteRay is not open source. We have plans to open source it, but it's not really a high priority for us right now. But if you're interested in it, I can definitely get you in touch with the author of it. Any other questions? Yes?
So what's the network overhead of distributing the data executable? Because if you're like going to run set of mapper job, you have to distribute it.
Right. I mean, it's really no different than the mechanism that's already in place for distributing non-shaded jars.
But most of the libraries are mostly in memory, or they are cached.
That is a good point. So the person here is pointing out that ByteRay's, the shading mechanism prevents Hadoop from caching jars locally and does lead to some increased I/O. So that's a very valid concern. Any other questions? Yes.
How do you decide to create a cluster? You said you have two clusters. So when do you decide to create a new cluster rather than expand the current cluster to make it share?
So I think a lot of it has to do with, so the question is, when do we decide to build a new cluster? How do we decide that it's time to build a new cluster? So one motivation for building a new cluster that we've seen in the past is that we want to have complete and total isolation between the dev and prod clusters and the new cluster, which will be used for some special purpose. I think there are a lot of new things that people are looking at using the clusters for, including things like TensorFlow, as well as other sort of like long-running services. And we have a pretty good understanding of how MapReduce or Spark jobs running in Yarn containers can interact and impact each other. We don't have much experience though with running other workloads on the cluster, and just out of an abundance of caution, we wouldn't want to co-locate those things until we sort of better understand what the impact would be. Yes?
What's your monitoring solution? Is it Dr. Elephant or is it something else?
The question is, what's our monitoring solution? So it is a collection of different things. LinkedIn has a great internal tool called Ingraphs, so that provides some monitoring for us. We also use Nagios, which I think a lot of people are probably here familiar with. And Dr. Elephant, like you said, also provides some monitoring for us. One sort of interesting thing about Dr. Elephant, which I'll just add quickly, is that when we built it, I thought one of the interesting things about it was that here is a monitoring or tuning tool which is really directed at users and user jobs as opposed to being directed at sort of viewing the cluster as a whole. So it's targeted at users as opposed to operators. But then once we got it deployed and set up, we found that the operators were actually kind of the biggest fans of this because it gave them the opportunity to stack rank jobs in terms of waste and then send nasty grams to the offenders. And I love ops people, but I've also noticed that one thing that gets them really excited is writing mean emails to people who are abusing resources. I think another interesting aspect of this also is that you have this shared resource, but the impact that individuals are having on others is not easy to find unless you put it in a public place. So we've seen sort of a lot of positive social pressure on people. You don't want to see your job at the top of the stank rag list because everyone's clear then, hey, this is preventing me from getting my stuff done faster. Any other questions? Yes.
Yeah, that's on that question. How do you separate the development team and choose the production team by the end of the
I think the question is, how do we separate our development and production workloads? So we actually run them right now on different clusters, although we're in the process of consolidating them into one cluster. One thing that we've invested in is making it easier to manage yarn queues. So we've added a feature that allows people to own their own queue, basically their own partition compute capacity, and then to subdivide that queue and assign those resources to the sub-teams that report to them. So the queues at LinkedIn very much look like the org chart at LinkedIn, which gives people a way both of ensuring, hey, this is the capacity that I've been allocated and I know that this is a guarantee. I think another interesting aspect of it is that it also makes it a lot easier then for these teams to do projections about the capacity that they'll need next quarter or the quarter after because they can express that in terms of what they currently have.
But in this case, you'll have some issues with the versions if you want to move dev, upgrade dev, but you want to keep prod as is because you're still testing it. Don't you see some issues with putting them on the same cluster?
I'm sorry.
Like you just said that you want to use the same cluster for dev and prod.
Right.
Which seems to be interesting in terms of compatibility if you move up for one version of dev.
Right. So the question is about the tension that exists between trying to consolidate everything on one cluster and having to pick multiple versions. I think one thing that I need to stress here is that when I say one grid, what I'm talking about is one logical cluster. It doesn't mean one physical cluster. So we want to eliminate the need for users to ever do migrations, to have to think about like, oh, I need to move my job from this cluster to another. So we'll have one grid, we'll have queues set up for dev and prod, and what's running underneath, is our concern, not that of our users. Yes.
You mentioned about for testing purposes, you take some jobs and then focus them on the same cluster. How much involvement you had to have of the team that owns the job in terms of the setup that you had to replicate? How did that?
Great question. So the question is, for SoapCycle, since we're taking workflows, actual workflows that are written by users, how much interaction do we have to have with the owners of the jobs before copying them over to the SoapCycle cluster, and how much help do we need from them in order to get them to run? So the answer there is that we don't have any contact with these teams, and that's by design, both because we don't want to waste their time asking them to help us get it set up, Another thing is we don't really want these teams to know that we are using their workflows for integration testing, because we don't want to create or generate the perception that this is sort of part of the contract. Like if you depend on some private API that everyone knows you shouldn't be using, and that private API changed, and now your workflow is going to break, that when we figure this out on SoakCycle, that we are somehow on the hook to solve that problem for you. So we don't want workflow owners to think about this as integration testing for their job. We want this very much to be integration testing for the services that we provide, and the workflow itself is just sort of a means to an end. Any other questions? Yes.
I think it's a great idea to run test flow for a name node as a Yarn application. I wonder whether you considered also running production HDFS this way.
I'm sorry, could you ask that one more time?
So you run HDFS data nodes as a Yarn application to generate test load of your name node, and I wonder whether you also consider to run it as a production service, like HDFS as a Yarn application.
Interesting. So the question is, with Dynamometer, we run HDFS as a Yarn application, and have we considered doing that for actual production use cases, like running HDFS in Yarn on our production clusters? And the answer is no, we haven't. And I guess it's not obvious to me what benefits that would bring, although I'd love to talk to you afterwards if you have some ideas about that. Any other questions? Nope. Okay, thanks everyone.